to my introduction on one of our next assignments here on quantifying uncertainty, the p-value, which this will be one of the next topics that looks into the historical significance of some of these concepts inside of statistics that we currently use nowadays. Specifically, the p-value in this case. This is one of the most important topics inside of this class due to the fact that, as we will see inside hypothesis testing in a bit, we obtain some p-value. We obtain a p-value. And one of the more controversial aspects about that is, what on earth does this p-value mean? But this p-value that we do obtain, it in this case refers to how unlikely some outcome is given some type of assumption, and that assumption is referred to as a null hypothesis. And specifically, this idea of p-values and using them the way that we've been using them were first developed within the 20th century by Pearson and Fisher, but these ideas themselves have been around for centuries, and typically inside of a court of law, these ideas are still in place to this day. But specifically, the idea though of where these ideas came from first started off as a concept known as a proof by contradiction. And a historian of statistics named David Bellhouse, he has characterized the 18th century ideas of probability using this proof by contradiction. And a proof by contradiction is a special way of proving mathematical ideas, which we are not looking at in this class specifically, but a proof by contradiction is what's used usually to make a proof about some type of especially hard concept, and then utilizing that to show the validity or invalidity of some type of statement. So, for example, the way that a proof by contradiction comes into play is within this part down here in our document. If we let A and B be logical statements, if the logical statement A is true, then the logical statement B is true. Okay? That's how we start off with. Then we show that B is not true. Therefore, the logical statement A is not true. But to exemplify that, and we'll work through this in this video, but let's suppose, for example, that a friend is rolling a die with an unknown number of sides. You predict it's a 6-sided die with sides numbered 1 through 6. Your friend announced that she had just rolled an 8. You would know that your prediction was incorrect. And we want to describe this example by defining logical statements A and B to set up a proof by contradiction argument. So we're going to let A. Let A be the following phrase. Rolling a 6-sided die. Six-sided die. Okay? All that is. In a similar fashion, we're going to let the logical argument B obtain a number let's say between 1 and 6. 1 and 6, that looks like a G. 1 and 6. 1 and 6, inclusive. Okay, so that means if we let A and B both be true, so if A and B are true, that means we are rolling a 6-sided die and we obtain a number between 1 and 6 inclusive. So we would roll a 6-sided die and obtain a number between 1 and 6 inclusive. But here we had that your friend rolled a 6. So friend rolled a 6. Which thus means that B then is not true now. Since 8 is greater than 1 through 6. Therefore, A is not true. So not a 6-sided die. Okay? So because, let me just fix this D as I talk. Because we let A be along a 6-sided die, since we just showed that B was not true, A is also not true, and it's not a 6-sided die, which is what this task 1 here was showing. So that's the main idea among task 1 in here. Alright? But, of course though, instead of mathematics, that's not the only way to prove something. We also have something called as a proof by the highly improbable. So this is what Bellhouse further suggested in the 18th century, that mathematicians started using a similar form of reasoning, but not specifically to prove a statement, but to conclude that it's very likely to be true. So here, if we let A be true, then B is almost certainly true. B is not true, therefore A is almost certainly not true. So do note, very similar premise to this, only difference being that now instead of stating that A and B are true, B is not true, thus A is not true. Now it's using this idea of almost certainly true inside of them. So let me erase all of this, and then we can work through task number 2 on here. For something characterized as a large eraser, it's not really that large, but what can you do? Not much. Alrighty. On that note, then. So proof by the highly improbable. So let's say, suppose that your friend with the die above now shows up with a suspicious looking coin and proceeds to flip heads 20 times in a row. Would you believe that the coin is fair? That is, would you believe that the coin will, in the long run, come up as heads half of the time? Why or why not? So specifically for that task 2, in this particular case, since it came up as heads 20 times in a row, I mean, is it possible? Yes. Right, but it's highly unlikely since when you flip a coin, typically it's supposed to come up roughly half. But 20 times in a row, though. So in this particular case, because of the 20 times in a row, so because heads came up 20 times in a row, it is, to quote this highly improbable idea, it is almost certainly not a fair coin. And then the third task here is to write the reasoning as a 3-part argument. So kind of like this part right here. So if we let A be A is, this is a fair coin. B would be that the heads comes half the time. Then we saw that B is not true, right? So since heads came up 20 times in a row, B is not true. Right, we have evidence of that since it came up 20 times. And then because of that, therefore, A, meaning where the coin is fair, is almost certainly not true. Again, due to that fact that heads came up 20 times in a row. And then the rest of this document here, which will be posted there up on Blackboard, goes up through this idea of what the historical significance of building up to this p-value is. First, as an example, with births and baptisms and the gender of the baby being, birthed and baptized. And then from that, going through stating a null hypothesis and what that looks like from a historical concept using Buffon's work, as you will read inside this document.